Oxidation numbers can be really helpful when trying to figure out when something has been oxidized or reduced. And there's some simple rules that scientists have developed in order to figure out how these oxidation numbers work and how they can be used. Now remember, in reduction and oxidation, it's all about transferring electrons. So we're going to look for changes to oxidation numbers when you go from reactants to products. But of course, to know what the changes are, you have to understand what the numbers mean. So let's just go through these rules real fast, and I'll try and tell you an example of how this works out. The first thing is that if you have a free element, which is just an element in its standard states, all of those will have oxidation numbers of 0. So if you have zinc metal, Zn solid, or oxygen as a gas, or bromine as a liquid, or any of the elements on the periodic tables, and again, notice none of those have ionic charges, positive or negative, then the oxidation number is going to be 0, and that'll be helpful to us. Most of the time, if you have a simple ion, the oxidation number just equals the charge on the ion. So if you had chloride, which is Cl -1, the oxidation number would be -1. And magnesium, which always has a +2 charge, would be +2 for the oxidation number. If you had an iron 3+ ion, then the oxidation number would be +3. On the other hand, if you had an iron +2, then of course the oxidation number would be +2. Now, the next two come in really handy. Oxygen is always -2, and hydrogen is always +1. Well, all right, here we get myself in trouble. I say always. In reality, there are some exceptions. Like oxygen, there are peroxides, like hydrogen peroxide, where oxygen's -1. And also when oxygen is with fluorine, fluorine is always -1, no exceptions. So with oxygen, and there are a couple of these kind of compounds, you can actually get into some positive numbers, but 99.9% of the time, oxygen is -2. And the same for hydrogen. Hydrogen's always +1, except, of course, there's an exception to hydrides. A hydride is a hydrogen with a -1 charge, so that would have an oxidation number of -1. Now, this is the important part. The sum of all the oxidation numbers will equal 0 for a compound, or the sum will equal the overall charge for an ion. And as an example of what I mean by that, let's look here at MnO2 in this example. Now you can see in the diagram that it's showing manganese is being reduced and the aluminum is being oxidized. But how did they get that +4 above the manganese? Well, remember that oxygen is 99.9% of the time, almost always, 99.9% of the time, -2. And there's 2 of them. So the 2 -2 oxygens plus the manganese is going to equal 0. This is a neutral compound. So if the oxidation number of manganese plus 2 times -2 for the oxygen equals 0, you can do the math real fast and see that manganese here is a +4. So that manganese 4 oxide has oxygen -2 for the redox numbers, and it has a +4 for the oxidation number for manganese. Now on the other side, you've got manganese by itself. This is elemental manganese, all right? And elemental manganese, like all the atoms that are free elements, will have oxidation numbers of 0. So your manganese is going from a +4 to a 0, and the only way that can happen is if it gains 4 negative electrons. That would allow it to go from +4 to 0. So that means your manganese is being reduced, all right? On the other hand, aluminum on the left, that's elemental aluminum, that's going to have an oxidation number of 0. And on the right side, the aluminum oxide, the Al2O3, oxygen, again, -2, and there's 3 of them. So it's like there's -6 overall charge. And those 2 aluminums are going to have to balance that -6 with a +6. So that means each aluminum is a +3. 3. So aluminum is going from a 0 to a positive 3. That means the aluminum on the reactant side is losing 3 electrons. It's becoming positive 3 in the process. So the oxidation numbers helped us to see that manganese was gaining electrons, being reduced, and aluminum was losing electrons, being oxidized. One final note on that reaction. Notice how the oxygen is -2 in MnO2 and the oxygen is -2 in the aluminum oxide. That means that oxygen was not reduced or oxidized, all right? It was necessary to make those things happen, but it wasn't actually involved in the electron transfer, and that part is important. So the aluminum, kind of boring in this, or the oxygen, kind of boring. The aluminum and manganese were the active parts being reduced and oxidized.
The atoms in hydrogen fluoride have oxidation numbers of +1 and -1 respectively. These are the charges the atoms would have if the bond were completely ionic. The oxidation numbers on the atoms of the perchlorate ion indicate the charges they would have if the transfer of electrons were complete. Such complete transfer, however, does not occur in reality.
So doing oxidation numbers does take a little bit of practice. The one on the left I don't think is too bad. Hydrogen and fluorine coming together to make hydrogen monofluoride or hydrofluoric acid, whatever. H, like we saw earlier, almost always +1, and that's definitely the case here. So fluorine then would have to balance that out with its own -1. Fluorine in compounds is always -1. There are no exceptions to that. But anyway, you see then that the +1 hydrogen and the -1 fluorine, those go to 0. HF is neutral, good to go. Now, for the other one, it's a little bit more complicated. ClO4 -1 is a polyatomic ion, and like always, oxygen, almost always, oxygen is -2, and there's 4 of them, so that's -8. Now, the sum of all the oxidation numbers equals the charge. So we don't know here the oxidation number of chlorine, but we have 4 oxygens at -2 because oxygen almost always -2. And the sum of those, the oxidation number of the chlorine and the 4 oxygens, in this case equals -1. That's the charge on the ion. So chlorine here, the central atom in this weird polyatomic, is going to have an unusual oxidation number. Now, normally chlorine, of course, is chloride, -1, but this is not normal chloride. So if you put the -8 on the right-hand side, it becomes +8, 8 minus 1. The oxidation number of the chlorine here, +7. All right, and so that's how you can figure it out. The only weird ones, in my opinion, are the central atoms and polyatomic ions. But if you remember that hydrogen's +1 almost all the time, oxygen's -2 almost all the time, you're good to go.